and welcome to this module. My name is Mehran and this is ML Dawn. Today we're going to start a module on the introduction to machine learning. And more specifically, these are the topics that we're going to cover in this module. So foremost, we're going to focus on the definition of machine learning. It is very common between people that sometimes they mistake algorithms with machine learning. So they just ask me that, okay, so why can't you just write a program that would do it? Why do you need machine learning? A program can easily accomplish a task. You can come up with a very efficient algorithm that could do it fast, and even in terms of storage and like time complexity, it would be efficient. Now, we will explain why that is not always the case. Actually, there are too many tasks out there that an algorithm can easily fail. I mean, by algorithm, I mean the solution is not for us to come up with a series of steps to write basically a computer program to accomplish a task. Later, we will talk about the examples of machine learning applications. And more specifically, we will talk about learning associations, where we're going to talk about the example of the basket analysis. Later on, we will focus on classification. And in classification, we will talk about different applications such as credit scoring, optical character recognition, face recognition, medical diagnosis, speech recognition, and so on and so forth. So they are all the applications, they're all applications of classification. Next, we'll talk about regression and how it can be used in applications such as robot navigation. Then we'll talk about the unsupervised learning, and we will compare it to the supervised learning, and talk about some of the interesting application of unsupervised learning, such as density estimation, customer segmentation, image compression, document clustering, and bioinformatics. And finally, we'll wrap it up with an introduction to reinforcement learning, and specifically where it can be used. It's one of the most common areas of reinforcement learning is game playing. And then we will explain why reinforcement learning is different from a supervised algorithm or an unsupervised algorithm. Why does it basically deserve to earn a new category? And finally, we will talk about, we'll basically give you certain exercises so that you would make sure that you got the materials. Right. Let's start by comparing the algorithm versus the machine learning. So, what is an algorithm? An algorithm is nothing but a series of instructions. So if I ask you, what is the algorithm of buying tomatoes? You would say, okay, I'm going to have to first take my wallet, make sure I've got money in it, dress up, go to the supermarket in my neighborhood, find tomatoes, buy them, and then pay the money, and then come back home. And that is how I buy tomatoes, right? I actually said tomato somewhere in the middle. I've been living in Ireland for some time. I think I've basically developed some sort of Irish accent. I have no idea. Anyways, so you see, that was the task. The task was buying tomatoes, and I can easily write an algorithm to do that, right? So an algorithm is nothing but a sequence of instructions to accomplish a task. For instance, let's go basically go more mathematically here. So imagine the example of finding the maximum in a sequence of numbers, right? So let's just give you an example, numeric example. So let's say we have basically an input, say x is 10, 8, 7, 1, right? And if I ask you to give me an algorithm that would find the maximum of these series, or any series, that algorithm has to be independent of my input. So any series of numbers that I give to the to your algorithm, it has to successfully find and capture the maximum, right? So then you would say, okay, my algorithm would basically first foremost would start from the beginning, right? Would take the first, actually this example would be a little bit too easy, so let me just put number 20 here as well. Okay, cool. Your algorithm would say, okay, get the first number. What is the first number? It is 10. Now compare it to each one of the numbers. So it would compare it to 8. Is it bigger? Yes. So still I'm considering 10 as my maximum. Now compare it to the next number, 7. Is it bigger? Yes, it is bigger. Now, again, I'm concluding that 10 is still my maximum. Compare it to the next one. Is it bigger? Yes. So 10 is still the biggest one. Compare it to 20, which is the end of my list. Is it still bigger? No, it's not. So, who's bigger? 20. So, 10 is no longer my maximum. Now 20 is my maximum, right? This is an easy example of how you can use an algorithm and set of instructions to accomplish a task, right? Now, not all tasks are this easy. There are certain tasks out there that you cannot find a straightforward algorithm for. When for a task you can come up with an algorithm, usually the relationship is not a one-to-one relationship. Basically, it's a one-to-many relation, meaning that for one particular task, you have different ways of coming up with instructions to accomplish it, right? Basically, you've got different algorithms, different algorithms to accomplish that. So usually you're looking for the most efficient algorithm. When I say most efficient, it means the minimum number of instructions or the minimum storage in the memory needed, or in terms of time complexity, the fastest in terms of time. So it depends on your needs, okay? Now, not every task has a nicely defined algorithm. A very simple example is, if I ask you to write an algorithm that would tell me how to differentiate between a spam and non-spam email, you can't. You know that the input to this task is an email, so I give you an email as an input, and the output would be 0 or 1. 1 meaning that, okay, it is a spam. Oh, oops, sorry. 1 meaning that it is spam, and 0 means it's not spam, right? So the inputs and the outputs are okay, we know that, but we don't know how to get from that input to that output. There's no evident way of doing this. You cannot come up with a series of instructions to do this. You see, the main reason for that is that the very definition of spam changes over time, right? And it's a subjective matter as well. What could be spam to me could be a very relevant email for you, right? So basically, we don't have the knowledge to come up with that series of instructions. However, even though we don't have the knowledge, we do have loads of data, right? So we have gazillion number of data out there that are actually spams, right? And we have gazillion number of data out there that are not spams, right? So basically what you can do is you will study all these spam emails and pay attention, because this is very important. We are getting basically to the core of this, the whole machine learning, the idea of machine learning. So we study thousands of spam emails and learn. Welcome. Learn what makes them spam. So there are certain signs in those emails that might be invisible to the naked eye of humans, but there are patterns out there, right? Basically, you would like your computer or the machine to extract the algorithm for this task automatically from what? From the data. So pay attention. We don't have that algorithm. We don't know what are the set of instructions to do this task. But machine learning says, give me all those data. I will learn how to do this. I will learn the features, the patterns inside those emails, and I will extract that unknown algorithm for you automatically. Okay? So what we lack in knowledge about the algorithm, we make up for by the data that we have, right? So this diagram shows this whole concept. So machine learning, remember, this is very important, actually very interesting. It extracts the algorithm from the data to accomplish the task. So you have loads of data here, right? And your machine learning, or ML, is applied to your data, and the algorithm is used. So this is step number 2. The algorithm is learned, okay? And then this algorithm is applied to the task at hand. That is number 3, right? So this would be number 1, step 1. So remember, we learn the algorithm. Okay, we learn how to. So basically, remember that is so after you do the learning, if I give you a test data, and by test data, we will work on these actually more. We will talk more into detail about this, but I just want to give you a very light insight. A test data is the data that your system has never seen before. So this test data is not in this box. What is in this box is called the training data, right? So using your training data that has loads of spam emails and loads of non-spam emails, your machine learning algorithm learns what makes a spam email spam and what makes a non-spam email non-spam. It extracts the algorithm, and then when you give it a test data, and a test data is a new either spam or non-spam email, right? Your algorithm is expected to successfully flag it, or basically, as we're going to talk about this later on, classify it into either spam or non-spam. It hasn't seen it before, okay? So again, the input are your emails, and the output are your labels, are your classes, namely spam and non-spam. Okay? Great. Now, moving on. Let's talk about some examples. Consider a supermarket chain, right? You've got millions and millions of customers. You've got millions and millions and millions of products, which makes a terabytes and terabytes of data. Okay? Now, I'm telling you that the task that we, say as the owners of this whole supermarket chain, are looking for is to predict who are the likely customers for a specific product. Okay, maybe I'm interested in finding out, okay, who are, say, the likely customers for a new computer that I've bought from, like, imported all the way from Japan. So that can help me to predict their needs. That can help me to come up with ways to introduce new products that would go well with my current computer, and advertise those new products to these potential customers. right? Because my algorithm is suggesting, sorry, my machine learning method is suggesting that, okay, these are the potential customers, so it's not a bad idea to also advertise these new products to them, as we know that these products are related, right? So again, the first question, is the algorithm for this task evident? No, it's not, because the environment changes as a function of time. It's not constant. Okay? People change, products change, the market changes, competitions change, and there are other factors in this whole story as well. Depending on the location, every person might have different needs due to God knows why. You know, when I say God knows why, there's a reason. Because we as humans cannot come up with that specific set of steps to make this algorithm, to make this task work. So algorithm does not, cannot make this work. We cannot come up with that algorithm. Let's put it that way. Okay? So there is a process that explains the data, and we hope to extract it from the data. We believe that the data is not totally random. You see, that is, machine learning is all about that. In your training data that we talked about in this slide, this box over here, this training data, we believe that those data are not totally random. We believe that there is a rule in there. There is a pattern there that is begging to be discovered, but we need machine learning to discover that. Okay? We can't even explain that pattern. Since we can't explain it, we cannot come up with an algorithm to explain it, right? And if we cannot come up with an algorithm, it means we cannot come up with a set of instructions. It means we cannot program it, so our computers cannot follow it, okay? Right. So we believe that there are patterns in the data hidden from the naked eye, but waiting to be discovered. Lovely. Now, machine learning in a nutshell. You see, in my data, there is a true unknown process, and we want to approximate it. Now, this is a little bit confusing, right? So I'm going to explain it into more detail. So if I have my input, say here, input, right? And I have the output. Let's consider the basically our first example, that I have an email as my input and I have spam or non-spam as an output, right? I just told you now that we believe that this mapping is not totally random. We believe that there is a rule, there's a pattern in my huge data set of emails that make each and every one of those emails either spam or non-spam, right? So there is a rule there. There is a process in this whole story that can take my input and can map it to either spam or non-spam, right? There is a process there. Let's call that process G, right? G gets your input, right? And it spits out your output. Namely, G gets your email and magically can tell you whether it's spam or non-spam, right? Now, let's go back to the first line. There is a true unknown process, so that is my G, that is an input and spits out an output. But we want to approximate it. Why approximate it? Because we don't know it. As simple as that, right? We don't know it. We know there is something there, but we don't know it. So we're trying to approximate it. So I want to focus on, I want to basically emphasize on this bit right here. We want to approximate our G or our true process, our true function. Okay? Now, can we do it perfectly? Usually not. Most of the time not. Right? But we are looking for a good approximation. a good approximation of this true process. So let me show it by f. So my approximation would be, let's denote it as f, right? F is an approximation of my true function, of my true process. Okay? Now, some of you might ask, okay, how do you approximate? How do you evaluate the quality of your approximation? Right? These are all questions that we will talk about later on. Maybe, probably not in this module. Probably, I'm not sure, I might include it later on. But maybe in the next modules we will cover how to evaluate your approximation. But for now, let's just say that our goal is to approximate the truth. Okay? Now, it can still detect and explain certain patterns, right? So this approximation might not be perfect, right? But it can still explain some of the patterns or some of the regularities in the data, if not everything. Okay, and that is usually what we end up with. We usually cannot come up with that perfect approximation, but we can come up with an approximation that covers, basically detects enough regularities in the data, enough patterns in the data that could accomplish our task, that could successfully map my input to the output. Okay, so this whole thing is the goal of machine learning in a nutshell. So the goal of machine learning is nothing but approximating the true function that maps the input to the correct output and nothing more. Okay? Very well. Now, let's talk about some of the applications of machine learning. So in finance, we are looking for building models for fraud detection, right? By the way, machine learning cannot just, doesn't have to be just limited to a database problem. Remember, in here, we talked about the data that we have at hand, and we will use it for training our machine, right? So remember that it doesn't have to be that way all the time. It can be also used for AI or artificial intelligence, namely the robot navigation in a changing environment. I remember that back in the days, I was watching the news and I saw these scientists that had built a robot that they were about to use to navigate inside the pyramids in Egypt. And in this particular task, machine learning could be really handful because they did not know that what type of a maze this robot is about to encounter with in the pyramid. They had no idea how the paths were, if it was slanted, if it was kind of dodgy or not. So you can easily use machine learning in that task. Well, when I say easily, not easily, but what I'm saying is it is an appropriate solution to think about. You can use machine learning for the robot navigation. Now in that case, again, you have, remember, you have inputs and outputs, right? So the input can be easily your the information about your robot. It can be the GPS information. It can be the angles of certain joints on your robot. It can be the current speed. It can be some data related to whether there's an obstacle on the right side, on the left side, in front of me, on my back side. What is the slope of the ground? So all of that would be your inputs, right? And the output can be directions, right? Should I go left? Should I go forward? Should I go right? Should I go backward? Should I jump? Should I sit? So again, as you see, there's an input and there's an output, and that environment keeps changing and changing, right? So remember, how many types of situations are we dealing with here? Meaning, how many types of environments could we be dealing with if you want to build a navigation robot? Infinity, right? It's not limited, right? So we do not want to, / we can't predict every possible situation and hard code it with its solution into our machine, right? Like if you saw an obstacle of this size in front of you, if the slope of the ground was like minus 30 degrees, if your GPS information was like around here, then turn right. Otherwise, if it was 29 degrees, if it was, you see, it's impossible. You can't account for all possibilities because you've got infinity and you got infinite number of possibilities out there. So the environment is dynamic. Again, this is begging for machine learning. So you've got loads of data that for every input you have the correct direction chosen, right? Then during learning, it will learn it will learn how to connect the input to the output. And guess what? When you give a test data to your robot, by test data I mean if you put it somewhere on a pathway that it has never seen before, it can kind of infer the correct direction because it has learned hopefully similar conditions, and it would pick the best according to what it's learned. You see, it really resembles how humans learn, right? Now, the other application would be computer vision, and it's about recognizing faces. Now, pay attention because this is very important. If I show you a picture of your uncle, right, facing right to the camera, and tell you that, okay, John, this is your uncle. Yeah, you're not, I mean, it's not hard for you. You can just easily understand that, okay, this is my uncle. Now, if you see your uncle in the rainy day, while he's just soaking wet, you can still recognize the face. If it's a sunny day and the sun is just covering the right sun, is shining on the right hand of his, on the right side of his face, and the left side is kind of dark and shadowy, you can still recognize his face. If he's like walking on his hands upside down, you can still recognize his face, right? If I ask you, how do you do it? The lighting is changing, the angles are changing, the positions have changed. How can you do it? You can't tell me. There's no way for you to explain it. And since we cannot explain it, we can't program it. Again, we're going back to the rivalry between algorithms and machine learning, right? So we can't explain it. We can't come up with an algorithm, but we know that the face image is not a collection of, please pay attention, random pixels. It's not. There is a pattern there. I mean, for starters, we're looking for some sort of a circular, like big circular thing in the picture, which is going to be the face. We're looking for two little radial shapes in the middle, which would be the eyes. We're looking for a vertical line, would be the nose. You see, you can come up with these rules that all the faces, no matter what the angle, what the lighting, what the position is, all of them have it, right? These things are called features. Those are the things that can describe your data the best. I mean, you're looking for those features that can explain your data the best, right? We will talk about the features in your data and how to extract them much more into details in the future modules. But I just don't want to, you know, cover the introduction for you, right? I want to also scratch the surface and tell you about some of the terminologies that are common in machine learning, so that when in the next modules we dig into details, you would have been familiar with it. Okay? So if it confuses you, don't worry about it. But I just want you to have heard them before actually hearing them for the first time in the next modules. Okay? So the machine will extract these structures about your face, right? And the patterns, sorry, there's a typo here. So the patterns, right? So this is called pattern recognition. So pattern recognition is one of the tasks, one of the, say, applications of machine learning, right? And here about finance, we talked about fraud detection. So again, it depends on your data. So if you've got loads of data in your finance related business that is related to non-fraud and loads of data related to fraud activities, you can again train a machine learning algorithm, algorithm to basically map those inputs to the outputs correctly. Remember, again, I'm emphasizing on this, there is a true function g that we are trying to estimate, we're trying to approximate using our machine learning techniques available, using our data, okay? So that is not going anywhere. That is the machine learning in its nutshell, okay? So in machine learning, the computers are programmed to, number one, optimize certain performance criterion using example data or the training data. Again, when I say optimize, remember that we are estimating the true function g using our model, right? Using our estimate. So basically our estimate would be f. We want to approximate g as good as possible, right? So basically I want to optimize this estimation, right? So basically every time I make my f better and better and better, right? The way it works is that every time I come up with an f, right? Say my f version 1, I have to evaluate how well am I doing. Say from like 0 to 4, I get 1.5. That's not totally bad, but it's not impressive at all. Say I do certain things to my f and come up with f version 2, and this time I get 3.5 out of 4, right? Now the question is what these numbers are. So, and what does it mean when I say I go from my f version 1 to f version 2, version 3, version 4 until I get to a, say, f star that approximates the true function the best, right? So I want to optimize this f until I reach to f star. And all I've got at my hand is training data. Remember, why do we need the training data? Because we cannot come up with an algorithm for that task, okay? Now, we assume a model which is defined using certain parameters. Just for those of you that are familiar, like kind of familiar with machine learning, I'll tell you that in a neural networks, or MLP, a multi-layer perceptron, the weights in the model that connects to neurons, those are the parameters of your neural network, right? For those of you who have no idea about the parameters, the neural network, all I'm going to say is this f right here is made of little bits and pieces, right? So f has certain parameters. Let's say, so f basically gets your input, right? And it has some parameters as well inside of it. I'm going to write it with params, right? So f1 gets the input that has some parameters. Again, the parameters are version 1. f2 will have, again, the same input, but the parameters version 2. And so on and so forth. Eventually, you'll come up with f star, that the parameters star, meaning that the parameters in your model, in your f, have been optimized. What does it mean? It means your f has now become the best thing that it could ever be. And it's a very, very nice approximation of the true process that explains how the input connects to the output, which is G. Okay? Now, when I talk about learning, I'm talking about the execution of a computer program to optimize these parameters using the example data or your training data, right? Again, I'm emphasizing on this, we are approximating the true process. So what is learning, my friends? Learning is learning those parameters. And every time you come up with a better set of parameters, better set of parameters, better set of parameters, your F becomes better and better. And the gap between your F and the truth, which is G, becomes smaller and smaller. Okay? So that is learning, basically. Now, the model that you'll end up with can be either predictive or descriptive. So predictive, the name implies that you're trying to predict something. Say, is this email spam or non-spam? Is this guy going to commit some fraudulent activities or not? So examples like this, right? But descriptive, it just wants to describe the data. We will talk more and more into details about that. I just want you to basically have heard these terminologies. Descriptive data, describing the data means I give you the training data and you would extract the patterns hidden in your data. Maybe you would talk about like different patterns, like you can tell me that, okay, give me your data and I'll tell you how many patterns, how many unique patterns are hidden in your data, right? Or you can give me the patterns that would make a spam email spam, or you can look at a picture of a face, right? And a descriptive model can describe what makes that picture a picture of a face and not a picture of a boat or a picture of a ship or a picture of a car, right? It describes that picture for you. It talks to you about the irregularities inside of it, right? And it doesn't predict anything. But a predictive model predicts, say, a class for you. Like, is this picture that you give to me, is this picture a picture of a dog, a house, or a lamp? Cool. And by the way, well, the examples that I come up with are very trivial. If I want to become more serious, I'll talk about, say, the oil price or the stock market, right? If I give you all the information related to the stock market up to today, can you predict the price of the stock of, say, Apple's, the Apple company for, say, in 3 days or in 7 days? Can you predict it for me or not? So these are the real applications. It's actually very money-making application of machine learning. Like if you could come up with a way to predict the oil price to an acceptable precision, you, my friend, you'll be rich, very rich. Now, the last thing that I want to talk to you about is the difference between machine learning and statistics, or basically the relationship between them. So which one uses which? Because that's a big question. Usually they talk about how the two relate to each other. Remember, machine learning uses statistics to build the aforementioned mathematical models. Remember the F that I talked to you about that has parameters? Remember I told you that we will evaluate it and we will make it better and better, and we change the parameters to make F as close as possible to the true process G, right? So it's a mathematical model. So why? Because the main goal at the end of the day is to infer knowledge from the data, or as statisticians like to call it, from the sample. They call the data the sample, right? So that is the goal at the end of the day. Perfect. I hope that you've enjoyed this course. I enjoyed it definitely because it's a very nice and gentle introduction to machine learning, and we will just smoothly transition into the next step, in which we will talk about the categories and other applications of machine learning, and we will become more technical. We'll talk about the learning associations, like if there are associations between your between different data in your data instances in your data set, in your database, how to learn that basically, and what learning association is. We talk about classification more technically. We will talk about regression more technically. We will describe some math to make you more familiar with the core of the concept. We talk about unsupervised learning and compare it to the supervised learning, and eventually we'll talk about the reinforcement learning. So can't wait to see you in my next class. So until then, on behalf of ML Dawn, take care.